Thanks, Andrew. Good morning, everybody. My name is Brett Borchardt, meteorologist with the National Weather Service in Chicago. And Lee Carlaw helped put together this presentation. He's working midnight shifts right now, so he will not be able to make an appearance. But this is a talk that we put together about the pretty devastating derecho that struck a good chunk of Central Region last year. I think most of us have heard about it by this point in time, but starting to do some analysis and put together some presentations about it so we can learn about what happened. This is a talk that was put together for the NWA conference last, I guess it was August. And so some of you may have seen these slides or heard this talk before, but this is going to be a slightly different one. I have a little bit more time than I had during the NWA conference, so we can delve into the details a little bit better. So without further ado, let me make sure my mouse works here, and we're going to jump on forward. All right, so let's talk about the derecho. So this is I think a now famous radar loop here. This is at least taken from I think our West display here. The derecho going across Iowa and northern Illinois. I think a lot of us have seen this radar loop in some way, shape, or form. But let's go over some fast facts. This was a behemoth of a storm. Derecho started in southeastern South Dakota, eastern Nebraska, and went all the way into western Ohio. And the damaging winds covered an area of at least 90,000 square miles. Within the 90,000 square mile zone, there are more than 20 million people that were impacted by the storm. That's a pretty sizable chunk of the U.S. population. There are more than 1 million homes and businesses that lost power within the damage path. And I think a lot of us know that that statistic is the customers, right? So that means that literally millions of people lost power after the storm. And some of the hardest hit areas, they were without power for weeks and even a month. And this is the middle of August, remember, so really not a good time to lose power. I guess there's never a good time to lose power, but August heat. And peak estimated winds were around 140 miles an hour in Cedar Rapids, but certainly greater than 100 miles an hour across large swaths. And the storm also produced at least 27 tornadoes, which is pretty ridiculous for one system to do that, supercell or QLCS or otherwise. The majority of those tornadoes, 15 of them were actually in the Chicago CWA, which is tied for the #2 biggest tornado event in our history. Ironically, it follows another derecho that struck our area June 30th, 2014, which produced, I believe, 18 tornadoes. So MCSs are big tornado producers across the Great Lakes, and this was no exception. Now, this was the costliest thunderstorm event in U.S. history. Recently looked it up, around $11.5 billion in damages, a lot of that to agricultural crops across the Corn Belt. Unfortunately, there were 4 fatalities and numerous injuries, and this storm wasn't well forecasted. I think we've all heard that by this point in time. Really had a lead time of less than a day. Even if you look at the Warren forecast model, I heard there's some victories claimed that the Warren forecast model had this storm. That's still a lead time of less than a day. So really just an incredibly impactful event with not a lot of lead time until the storm's actually developed. And I think the storm is going to be sliced and diced in the research world for years, if not decades to come, just as the 2012 derecho was, since this is obviously a huge target of opportunity for additional research. But today, the way we're going to slice and dice it is we're going to look at the damage produced by this storm. And this is a map that was created by Scott Lincoln. He's the senior service hydrologist in our office, and he collaborated with many of the impacted offices, looking at the estimated damaging wind swaths that's shaded there. And we also have tornado tracks that are plotted as well as the contours. And what's absolutely remarkable, #1 is just the spatial extent of the damage. But #2 is the way that the damage changed across northern Illinois. So from western to Iowa to western Illinois, you had a relatively compact zone of damaging winds. We're looking at 3 to 4 counties wide. And within that swath, there's fingers of 100+ mile-an-hour winds, especially across eastern Iowa there. However, when the storm went into northeastern Illinois, the winds actually lessened in intensity, and they became most intense in narrow swaths, little fingers of damage. And within those fingers of damage, tornadoes were pretty common. In fact, again, 15 of those just in northeastern Illinois and northwestern Indiana alone. And then the spatial footprint of the 60 mile-an-hour wind gust increased in size as well, encompassing really a good chunk of northern Illinois as well as northwestern Indiana. Now, this change was not anticipated. For better or worse, I had the benefit of working this day. And as we saw the storm barreling through Iowa, we fully expected it just to go unimpeded, just a bag of wind to come through northern Illinois. Honestly, tornadoes were not really on our minds. And we didn't anticipate this transition in the storm, the transition in the damaging winds. And it's important to understand and anticipate these changes, because if we can anticipate a change in storm morphology, or really the damage, a change from damaging winds to tornadoes being a predominant threat, that's critical information that we can pass on to our partners as well as the public. I think we all know the Mesoanalyst Boot Camp has done great strides in this regard, and this fits really nicely into that to figure out why exactly the derecho changed. So the way we're going to examine this is we're going to do some good old-fashioned radar analysis. I have a couple radar loops here, and on the left is the data from the Quad Cities radar just west of the Mississippi River. And on the right-hand side is data from our WSR-88D in Romeoville, Illinois, or Lockport, Illinois. And the way this was created was we actually loaded this up in the west, and then we used the same scale, and we're really careful not to move the mouse. So that way we can look at the system, again, at the same scale here. You'll notice that the shape of Illinois there, if you look at the blue line, it's kind of hard with a split screen, but the blue line is exactly the same there along the Wisconsin border. So this gives us the opportunity to compare and contrast the system really just 2 hours apart. And the most striking feature to me is the fact that this looks like two completely different storms on two completely different days or years or decades, right? On the left, we have a very compact bow echo, really pronounced mesoscale convective vortex. On the right, we have much more elongated QLCS. This looks like this could even be along a cold front if you ignore the the MCV along the Wisconsin border there. And these radar loops were taken just 2 hours apart. So it's just remarkable the change in the structure that occurred really over such a short distance. If we throw on some annotations here, I just want to talk about this a little bit. Across Iowa, just a classic bow echo, classical in the sense of, this is almost what you see in papers for classic damaging MCSs. Really pronounced rheum flow jet, rheum flow notches, nice mesoscale convective vortex. Even had a nice warm advection wing. I wonder if I could throw on actually a spotlight here. I'm not sure if that's showing up. Well, anyway, warm advection wing near the Wisconsin border there. Actually had some embedded supercells produce a 2-inch hail in Freeport, Illinois, as well as 2 tornadoes in Rockford. So just even a strong kinematic environment for supercells. If you compare that to the frame on the right, it looks very different, as I mentioned. You still have a pronounced rheum flow jet. It's a lot broader though, and you have a much larger section of the QLCS that's balanced. Now, what are we talking about? No balanced. Let me see if I could. There we go. I have my pointer turned on. Just as a reminder, when we're talking about balanced, shear dominant, cold pool dominant, this is what we're talking about. We're talking about the updraft, and this is a very basic interpretation of how updrafts develop in squall lines. Obviously, there's a lot more that dictates this, but we want to boil it down to the most basic components. There's prevailing school of thought there that there's always this balance between the cold pool and the low level shear, right? So if you have on the bottom diagram here, if you have just a cold pool with no shear at all, this is like a classic day in July or August in the deep south. You develop a cold pool, it splats out, and your updrafts become rearwardly sloped over that cold pool. On the flip side, if you have a lot of shear, your updrafts can actually tilt, as we say, down shear. That becomes shear dominant. And the optimal balance is when the low level shear is more or less balanced with the cold pool, and that leads to vertically erect updrafts. And the reason why these updrafts are really important to be just vertically erect is number one, vertically erect updrafts are the strongest that they can be. There's some studies out there, one especially from Matt Parker, who showed that vertically erect updrafts in squall lines are optimally taking advantage of instability. You get the most bang for your buck with CAPE. But that also means that you get really good low-level stretching. We all know that low-level stretching is important for the development of low-level circulations. If you have a really strong updraft, you get that low-level vacuum, bada bing, bada boom, you have stretching. Of course, low-level shear is also important when it comes to nonlinear dynamic perturbation pressure gradient accelerations by virtue of, again, creating that low-level vacuum to suck up low-level horizontal vorticity. So this balance between the cold pool and low-level shear is really critical when it comes to the intensity of squall lines. So that's what we're talking about with balance. That's why we talk about balance sections of QLCS with the 3 ingredients method. This is what we're looking at. Moving on, I do want to look at the velocity here, mainly because it's if you want to say eye candy. If you look at the velocity across eastern Iowa there, it's absolutely nuts. We're talking about returns of 100 to 110 knots coming right toward the Quad Cities RDA. And while I had my hands quite full in Chicago, I would have loved to be a fly in the wall in the Quad Cities office just to hear their disbelief as this was coming toward them, because it really is almost unbelievable. If you compare that with the velocity returns across Illinois, it's very different, right? we still have a pronounced rear inflow jet, a very broad rear inflow jet. We're still looking at those light blues, that's values of 60 to 70 and pockets of 80 knots. Still very easy to issue a warning, obviously producing severe winds, but it's a lot less focused, it's a lot less intense. And if we were to zoom in to the velocity from the Chicago radar, and if we convert it to storm relative velocity here, remove the storm motion, throw on some circles here, you'll notice that we actually have persistent low-level circulations. A lot of times we call these mesovortices, mesocyclone circulations, they're all the same thing. Dynamically, they develop the same way. And if I were to do some PowerPoint magic here and track them forward, you'll notice that the circulations, again, while persistent, correlated pretty nicely to these fingers of damage. And that's probably not a surprise, especially to veteran forecasters out there who've stared down the barrel of a lot of these QLCSs. Circulations within squall lines are responsible for some pretty high-end damage, especially at the superposition of the rear inflow jet and the rotational velocity. So the right side of a circulation with respect to the forward motion, that's a hot spot for really high-end wind damage. Whether that damage is spinning at the ground or in what we call a straight line doesn't really matter. It's really high-end wind damage. And certainly these are what were responsible for these fingers of damage across Illinois. In between these circulations, there still was damaging winds. You'll notice one of those circulations was precariously close to our office there. Our office is co-located with the radar. And while thankfully it missed our office, we had our backup office on standby. We still had severe winds at our office. We still had tree branches flying outside the window. So, it's pretty interesting that these circulations were prevalent as it went into Illinois. And that's, I think, easy to say that was responsible for the fingers of damage. So we just take a quick step back here, just talk about what we've talked about with the radar analysis. The Derecho evolved pretty rapidly from eastern Iowa into Illinois, from this compact bow echo into this really elongated QLCS with this large balance zone. And the damage across Iowa was largely driven by that descending rear inflow jet, 110 knots, right? As well as the southern side of that mesoscale convective vortex, which prolonged the duration of the damaging winds, some areas longer than an hour. While the damage in fingers across northeastern Illinois, northwestern Indiana was driven by these low-level circulations. That's great, perhaps not surprising, but we still haven't even scratched the surface on what led to the structural changes of the derecho. And that's really the question I want to hone into here. So what I want to do next is I want to start looking at some model data and observations to help explain this. And what we're first going to be looking at here is we're going to be looking at some RAP data, the RAP 13. The next few plots, we're going to be looking at MRMS radar mosaic, that's the RALA radar at lowest altitude. And then here is the 0 to 10 kilometer shear that's shaded, contoured, and barbed from the RAP. And the reason why we're looking at 0 to 10 kilometer shear instead of, let's say, 0 to 6 kilometer shear is because this is the beginning of August. Our equilibrium levels were like 15 kilometers, really, really high up. So we want to look at shear over a very deep layer over what the storm is going to be feeling. In addition, a lot of contemporary studies have demonstrated that 0 to 10 kilometer shear is fantastic at discriminating environments that are supportive of intense mesoscale convective systems versus not so intense mesoscale convective systems. So for that reason, we're going to be looking at shear over a very deep layer. And I'm going to animate this going forward here, and we're going to see at least how the RAP analyzed the shear going forward here. And you'll see that we had more than sufficient deep layer shear. We're talking values well greater over 30 knots, even pockets of 55 knots as it moved into Illinois. One could say there was a trend of decreasing deep layer shear with eastward extent that likely had to do with the departing upper level jet streak, but nevertheless, it's still very favorable. Now, of course, there was a gradient in the deep layer shear with southward extents. I think we all know that nothing is infinite. Shear is not infinite across a meridional plane, so there's always going to be some sort of gradient in shear. And you notice in the MRMS radar reflectivity, you had less robust updrafts on that gradient of shear, likely because you just had a not so favorable kinematic environment for intense updrafts. What we're going to look at next is a 0 to 1 kilometer shear. So now we're going really down close to the ground. The reason why we're looking at 0 to 1, I think as we all know, is 0 to 1 kilometer shear and even smaller layers, 0 to 500 meter shear, is well correlated with environments that are supportive of low-level mesocyclones, low-level updrafts that can tilt and stretch low-level vorticity. And what's really interesting is the 0 to 1 kilometer shear, at least what the RAP was analyzing or suggesting this day, was really not that strong. We're only looking at 10 to 15 knots. Certainly, that's not zero, but it's not the values you would typically see on let's say, a really big tornado outbreak day in the plains or the deep south. So right off the bat, when you're thinking about tornado potential, if we're only looking at 0 to 1 kilometer shear, you could almost write that off because it just doesn't seem like you have the shear necessary to develop those strong low-level mesocyclones. On the contrary, if we actually look at a slightly deeper layer of shear, but still in the low level, 0 to 2 kilometer shear, it was a completely different story. And you'll notice that the 0 to 2 kilometer shear increased rapidly ahead of the derecho as it moved into northern Illinois. We're going from values of 20 to 25 knots across Iowa to values of 30 to 35, and even pockets of 40 knots of 0 to 2 kilometer shear across northern Illinois. And that certainly was co-located with the section of the system that became balanced. And in fact, the 0 to 2 kilometer shear does a really good job discriminating different sections of the MCS here, most predominantly along the southern section of the derecho. Notice how that's cold pool dominant. That's where your low level shear simply cannot balance the cold pool. We have a heck of a cold pool here, right? It's the middle of August. We have a lot of latent heat release, a lot of precipitation, very deep cold pool. And we talked about the cold pool low level shear balance earlier. That balance was simply not there across central Illinois. So you have that inflection point across, I guess, north central Illinois, that southern dotted line, and then you have this really large balance section. And I think this actually very nicely describes why we had that elongation in the balance section of the MCS. In addition to helping describe perhaps why we developed those persistent low-level circulations, again, we had stronger low-level shear, strong low-level nonlinear dynamic perturbation pressure gradient accelerations. Now, of course, we've just been looking at model data here. It's really good to look at observations to make sure that the model was at least in the neighborhood of what happened. So what we're going to look at now is the vertical wind profile from our radar in Lockport, Illinois. These were generated from some scripts that Lee created. I think if anyone knows Lee, he's an absolute wizard when it comes to coding. So time is going to go from right to left on this plot here, and then the height is in kilometers. I'm going to annotate here the gust front passage at our office here is at about 2036 Zulu. And before I go on any further, those black barbs there, from like 2022 to 2029 Z at 2 to 3 kilometers, we think that's bad data. The root mean square errors were approaching like 10 knots at that time, and we think we may have actually been sampling some winds associated with the mesocyclone really close to our office. So we're going to ignore those right there. Instead, what we're going to do is we're going to highlight this layer from about 1.25 kilometers to 2.5 kilometers. And notice how the wind speed increased. It's not dramatic. It's not like we went from 30 knots to 80 knots, if we're excluding the bad data there. But we went from the low 30s, let's say 32, 35 knots, to the mid 40s, 42 to 47 knots, especially at 2 kilometers. And that certainly helps explain why the 0 to 2 kilometer shear increase. It looks like the RAP at least had a decent idea of what happens there. And notice that this is entirely below 3 kilometers, entirely above 1 kilometer. So looking at traditional shear layers like we were doing on this day, completely missed it. We completely missed the fact that the flow was increasing at 2 kilometers. So at the back of our minds, we were not even anticipating tornadoes. Just a quick aside here, when it came to warning strategies, the way we had it set up was we had one person focusing on severe warnings, and we had someone else who's going to be sort of a backup to help out with those, and also kind of the token tornado warning person for severe weather. We were not anticipating having to issue any tornado warnings this day, and we ended up issuing quite a few. So it's just remarkable that this increase in flow occurred in a layer that we traditionally were not looking at. Another way we can visualize this is by looking at Horographs. These are VWP-derived Horographs at our terminal. I guess it's not ours, the FAA terminal Doppler radar at O'Hare. We're very lucky where we have several radars in our CWA that we could take advantage of, but using a different data set here to show that it's not just one point, it's not just from our VWP, this is another radar. And you can see from, I should also explain, on the left, that is about 1 hour before the line made it to O'Hare. On the right, that's about roughly when it made it to O'Hare. So we're looking at a 1 hour difference in the wind profiles here, and I have the 0 to 2 kilometer shear vectors kind of sketched in here. And you'll notice that, lo and behold, the 2 kilometer flow increased. We went from around 30 knots to say 38 and 37 knots, 7 knot increase near the level shear right off the bat there. And you can see that annotated in the table in the upper left. And one other final way to hit this point home is this is kind of a unique plot that Lee made. We're going to be looking at air speeds through the 6,000 to 8,000 foot layer that's at about 2 kilometers. And these are wind speeds measured from aircraft that are actually going through that layer. And this is going forward in time. And the bar graph, or not the bar, the line plot that's also plotting the upper left there, that's going to be the average wind speed, the mean wind speed in knots of every single point that you're seeing in exact time. And I think it's pretty evident here in the hours preceding the derecho, the flow was relatively weak. We're talking about 16, 17 knot wind speeds at 2 kilometers, but it increases dramatically in about the hour preceding the derecho. The mean wind speed goes up to over 30 knots at 2 kilometers. And that just verifies what we were seeing at the VWPs from our radar and then the O'Hare FAA radar. And that, again, pays homage to what we were seeing in the RAP data. So we basically had an increase in our low-level flow preceding the derecho. Now, the million-dollar question is, why did the low-level flow increase? And I don't have a good answer for that today. And that's something that we're looking at and actually working with a few others on that to see if we can explain why the low-level flow increased. But one thing that we can look at is, if we remember back to our undergrad or grad school days, if we talk about potential vorticity, this is a very simplified diagram of potential vorticity. If you have a lot of latent heating, really strong convective towers, if you go by the potential vorticity school of thought, that demands that you generate basically a PV max, or basically a low pressure system below that center of heating. And a lot of times, I think as meteorologists, we like to put different things in different boxes. We say mesovortices happen in squall lines while mesocyclones happen in supercells. In reality, the atmosphere doesn't really care. Dynamics don't change because you have a different storm mode. The atmosphere still behaves by the governing equations. I think the same thing is true here. We have a low pressure system that's generated by convection, but it's nevertheless a low pressure system. And one of the analogs for tornado events, at least in northern Illinois, but I think across a good part of the country, is a deepening low pressure system is never a good thing, right? That leads to increasing low level flow, increasing low level shear, and increasing parameters for low level mesocyclone development. And I think that's likely a contributing factor here, is the fact that we had a deepening low pressure system going across the Illinois-Wisconsin border, and that likely led to an increase in the low level flow. Now, why the low level flow increase was only confined to the 2 kilometer layer, I don't have an answer for that. I think that's an interesting question. Maybe that's where if you do go from a PV school of thought, that's where the greatest response would have been seen. I think a potential vorticity inversion would be really interesting for this case, and that's something we're sort of exploring doing. It's kind of code heavy, but we're looking into it. And this is not necessarily unusual. We've actually had a number of cases do something similar to this QLCS across northern Illinois. Most notably, an event this past June, we had an EF3 tornado in the Chicago metro. It actually passed about a mile south of where I'm sitting right now. And this is another environment that it changed rapidly, really just ahead of the QLCS. And if I just annotate the storm passage on here, this was June 20th of this year, you'll notice the low level flow increased from the low 40s to the low 50 knot range preceding the line of storms. And that's a pretty notable increase. Of course, 40 knots versus 50 knots at 1 kilometer is kind of, I don't know if it actually matters because it's still really strong anyway. But if you look at the Horograph in the upper left hand side there, the 0 to 1 kilometer SRH was like 600 joules per kilogram. That's just ridiculous. But it just hits home that maybe this is somewhat similar with squall lines that produce tornadoes. Maybe they alter the environment, and that's a question that we're going to be looking at a little bit deeper here. And I do also want to mention, if you guys haven't seen this page, this is maintained by the Storm Prediction Center. Their internal, their WOC page, sbc.woc.noaa.gov. You can only access it if you're on the network at your offices. But I believe this page was developed partly in response to the after action review from the derecho, since when we noticed that 0 to 2 shear increase, we were like, hey, we need ways to be able to visualize this in real time. And I think we answered the call here, and this is a fantastic page that was developed by them. It updates in real time, and it's a tool that we always have up on our displays anytime we have severe weather in our CWA. So I highly recommend everyone check it out. Anyway, if we get back to our system here and wrap this all up here, just to summarize everything we talked about, we first looked at the radar analysis. The derecho evolved from that compact bow echo into an elongated QLCS with a large balance zone. And I think a lot of that was due to the spreading of the cold pool along the shear gradient in central Illinois. And again, we talked about the increase in the low level flow and why that may have occurred. It just seems like this was perfect for a larger balance section that was more favorable for strong vertically erect updrafts that can stretch low level vorticity. And to tie that into point 2 here, the damage across Iowa was largely driven by the descending rear inflow jets. I strongly suspect there were more tornadoes. We just can't survey them. If you have, a EF0 tornado followed by 100+ mile-an-hour winds, I guess it doesn't really matter. But the fingers and damage across Illinois were largely driven by those low-level circulations. Those developed in tandem with the increasing 0 to 2 kilometer shear. Now, throughout my rambling here, I think the number one point I hope everyone can take away is to make sure you scale your mesoanalysis to the environment and the storm. Don't necessarily rely on those traditional layers like 0 to 1 kilometer shear or 0 to 3 kilometer shear. Don't necessarily look at CAPE as just a number. Where's the temperature difference greatest? Is it in the hail growth layer, et cetera, et cetera. I think that's critically important to developing a good understanding and an expectation for how convection is going to behave, which of course we can translate into really good IDSS to the public and partners. So that's really the number one takeaway I hope everyone can take from this presentation. So with that, I think I will wrap up here, and if anyone has any questions, I'd be happy to take them.